For this classic optimization problem, we're going to be looking at a person who wants to run part of the way to an island on land and then finish the trip by swimming. So maybe this is someone who's doing a triathlon and they have to do the running and swimming first and the biking last when they get to the island. Something along those lines. So the problem says an island is 2 miles due north of its closest point along a straight shoreline. A visitor is staying in a cabin on the shore that is 6 miles west of that point. The visitor is planning to visit the island. Suppose the visitor runs at a rate of 8 miles per hour and swims at a rate of 3 miles per hour. How far should the visitor run before swimming to minimize the time it takes to reach the island? So we have all of our water with our pretty island out here. Here's our island, right? And we have our shoreline. And here's maybe our cabin with our person in it. And here's all of our lovely water. So our person wants to run along the shoreline up to a certain point and then jump into the water to swim to the island. We know that the island is 2 miles due north of the shoreline. We know that the cabin, this total distance to the cabin, is 6 miles from the point where the island would meet the shoreline. So what we need to figure out is how far does our person want to run before they start swimming? So if we call their running distance here x, and we call their swimming distance here y, that's how far they swim from the shore to the island, then we can figure out how to minimize their time. That's our objective. We want to minimize the time that they take getting from the cabin to the island with a mixture of running and swimming. So there's no way to only run because it would only be going due east and they would never get into the water and get to the island. They could do all swimming if they just jumped in from the cabin, but they swim much slower than they run. So it wouldn't make sense from an optimization point of view to only swim. So what we need to do is label a few things. So we know that x is our running distance. So let's write a few of these out. So x is our running distance. Y is our swimming distance. So let's get those marked in first. Well, then we can also say that the rate at which our visitor swims is 3 miles per hour. And we can say, let me find a different color here. There we go. The rate at which our visitor runs is 8 miles per hour. That's pretty fast. So what we want to do is remember that distance equals rate times time. So let's remember this. Distance equals rate times time. Or if you want to think about it in terms of rate, you've got things like miles per hour, feet per second. That is a distance per time. So it's the same idea. So what we're going to do here is define each one of these. So the distance that we run here, that our person runs, is going to be the rate for running, which is our red. So the rate that they run times the time that they run. And the distance that they swim is going to be the rate at which they swim times the time that it takes them to swim. So we're trying here, if we read the problem statement, we want to minimize the time it takes to reach the island. Well, that time is made up of time to run and time to swim. So we're not going to minimize the running time alone or minimize the swimming time alone. We want to minimize the total time it takes them to get to the island. So what we need to do then is we need to solve for time in each of these instances and know that our total time is going to be both of them added together. The time that our person spends running plus the time our person spends swimming to get to the island. So let's do that. So here, our time to run, which I'll go ahead and put in red as well, is going to be the distance that they run over the rate that they run, just by solving for t. So that is x over 8. And the time it takes for them to swim is going to be the distance they swim divided by the rate at which they swim. In this case, that was the y over 3. So now we have the two components to our time, and we can then add them together to find our function that we're trying to minimize. That would be our objective function. So let me scroll up just a little bit here so I can write it in. So we do know our objective now. Our objective function is we want to minimize, right? Minimize the total time. So what that means is we say that our total time, I'm going to call it big T, is going to be the time it takes to run plus the time it takes to swim. And in this case, that's equal to, well, the time it takes to run is x over 8, and the time it takes to swim is y over 3. Or if we wanted to rewrite these as a fraction times the variable, we would say that this is 1/8 x plus 1/3 y. And the reason that might come in handy is in a moment when we solve for a constraint variable where we can find y in terms of x, then we can plug one in and we're going to end up needing to either multiply it by 1/8 or by 1/3 depending on whether we solve for x or we solve for y. So that's where we need to start in with our constraints. So let's think about a few things with our constraints. So with our constraints, we have things like the running distance, x, has to be between 0 and 6 because there's no more than 6 miles of shoreline between the cabin and the island, right? And we know then that there has to be some relationship between x and y. Otherwise, we couldn't solve our problem. So now we need to figure out how to find that last constraint. So we have to think about what's happening in our triangle. Let me find my thing out here. So if we look at this triangle, oops, let me put it back on pin. There we go. All right. There we go. And I don't have the shape tool on my app here that I do on GoodNotes when we're in class. So bear with me if my triangles aren't beautiful. So in this case, we know that our hypotenuse is y miles, our height is 2 miles, and we don't know what the base is. What we do know is that the total length of the shoreline that we have available is 6 miles. If the part that we run is x, that means the part that we don't run has to be whatever you add to x to get 6. So it would be 6 minus x. It's what's left over. It's that total of 6 minus the piece that was run. That's how we find the piece that was not run. We just take the total number of miles, 6, and we subtract off the part that was run. And so now we can come up with a constraint equation that in this case will be a Pythagorean equation. So what we'll say then is we can see then that 6 minus x squared plus 2 squared has to equal y squared. This is our other constraint. And this is also one that we can then solve for y. So we need to make sure then that we also state that y has to be greater than or equal to 0. But in this case, if they want to reach the island, it can't even be equal to 0. It has to just be greater. Because if they never swim to the island, right, then that would be a problem. If y is the distance that they swim, and that's 0, that means they never made it to the island, so it wouldn't fit the scope of the problem. So again, we're trying to base our constraints, which in this case are related to our domains, our domain here in the problem. We're trying to relate it to actual physical problems. So now we know then that the distance that they swim has to be greater than 0. So we're going to say, okay, then let's see what happens if I solve for y. So I'm just going to switch them around and rewrite it as y squared equals 6 minus x quantity squared plus 4. So that means y has to be plus or minus the square root of 6 minus x quantity squared plus 4. Well, 6 minus x quantity squared will always be positive because it is squared, and 4 will always be positive because it is squared. So in a very physical sense here, we cannot use a negative square root because then we would have a negative value for y. And we can't unswim, if you will. So we have to make sure that y is always positive. So we're only going to use the positive square root here of 6 minus x quantity squared plus 4. And now we can take that and plug it back into our time equation, our objective equation, and see if we can come up with a solution. So if we go back to our objective equation, t, we're now going to make it a function of x because we're replacing y with a function of x. So it's going to be our 1/8 x plus our 1/3 times the square root of 6 minus x squared plus 4. So it looks kind of ugly, but we're going to make it okay. We're going to rewrite it, we're going to take our derivative, and we're going to solve for any critical points. So let's see what we can come up with. Let's first rewrite it, and I'm gonna rewrite it this time all in one color. So I think I'm gonna go back to the black pen here so we can see it all in one color now that we know where all the pieces came from. So we're gonna rewrite t of x is going to be 1/8 x plus 1/3, and we can rewrite 6 minus x quantity squared plus 4. We can throw it into some parentheses and raise it to the 1/2 power because remember the square root has a rational exponent of 1/2. At this point, we're ready to take our derivative. So if we did t prime of x, we can say then the derivative of 1/8 x with respect to x is just 1/8. Plus, and 1/3 is a constant, so we carry it down with us. And for the rest of this expression, we're going to have to use our chain rule a couple times. So first things first, we're going to bring down our 1/2 power. So times the 1/2, and that means we do this 6 minus x quantity squared plus 4, and we have to raise it to the 1/2 minus 1, or negative 1/2. Then we have to deal with the derivative of the inside. So that would be 2 times 6 minus x, now to the 1, and the derivative of 4 is just 0. Right? So here we're going to do, let me highlight some more of these other things that are still color-coded. And so our derivative of the inside is this guy. And then what happens is we also now need to multiply by the derivative of 6 minus x because we took a derivative of 6 minus x quantity squared. So we have one more derivative in here, which is the derivative of 6 minus x, which is just negative 1. So that's a lot of chain rule all in one place. So just remember, if you're taking the derivative of an expression, you always have to multiply by the derivative of what is inside the expression. Okay, and we did that twice here. So if you're following along, then now we're at the point where we can set it equal to 0 and try to find our critical points. So we set it equal to 0, and we have 1/8, and now we have 1/3 times 1/2 times 2 and times a -1. So it's going to be a subtraction because there's only just the one negative. But what happens is the 1/2 and the 2 multiply to give us 1. So we've taken care of the 1, we've taken care of the 2, and the 1/2. So now we're only left with 1/3. We still have that 6 minus x, and we still have this 6 minus x quantity squared plus 4 all raised to the -1/2. So one more time, we took 1/2 times 2 gives us 1. 1 times -1 gives us -1, and -1 times 1/3 gives us -1/3. Right? So just a reminder, what we did here is we said 1/3 times 1/2 times 2 times -1. Those guys canceled out, and it equals a -1/3. And that's where this guy comes from. So now we can move what's on the right over to the left because it's the negative. So we can say then that we've got 1/3 times 6 minus x times 6 minus x quantity squared plus 4 to the -1/2 now equals 1/8. And if we rewrite the left-hand side a little bit here, we can rewrite it as, well, the 3's in the denominator, the 6 minus x is in the numerator, and the square root's going to go into the denominator because it has a negative exponent. So we would just have 6 minus x over the 3 is still in the denominator, and this root of 6 minus x quantity squared plus 4. And it equals 1/8. And this is where our handy-dandy cross multiplying comes in, where we have a fraction equal to a fraction, or a rational expression equal to a rational expression. So we do 8 times 6 minus x, and we do 1 times 3 is just 3 roots of 6 minus x quantity squared plus 4. And this is where we can do some more of the fun things, where we can now square both sides to get rid of the square root. So 8 squared is 64, and then 6 minus x, the whole thing is squared. 3 squared is 9, and it's times everything that's under the square root. So it's times 6 minus x quantity squared plus 4. So if we do a little distributing on the right, we end up with 64 times 6 minus x quantity squared equals 9 times 6 minus x quantity squared, and 9 times 4 is 36. Well, now we're about to do something really fun. We get to combine like terms. So we have 64, 6 minus x squareds here, and we have 9, 6 minus x squareds on the right. So we're just going to subtract it over. So we're going to say, let's subtract 9 of these 6 minus x quantity squares. So I had 64, I removed 9. So I am left with 55 of these 6 minus x quantity squareds, and it equals whatever's left on the right-hand side, which is just 36. So if we divide both sides by 55, we get 6 minus x quantity squared equals 36 over 55. And now, in order to undo that square, we're going to take the square root of both sides. So we end up with 6 minus x quantity squared, and then we square rooted it, means that it's just 6 minus x. And on the other side, we're going to have plus or minus the root of 36 over 55. But we can rewrite that a little bit because the square root of 36 is 6. So it'd be plus or minus 6 over root 55. So if we solve for x by adding it to the other side and bringing 6 over root 55 to the left, the x to the right, and switch them around, we end up with x is equal to 6 plus or minus 6 over the root of 55. So now that we have two different possible values, we usually automatically throw out the negative square root. But what we're going to find is that 6 over the root of 55 is small, fairly small, in relation to the 6. So we're not going to get a negative value when we plug in the negative square root. We're going to get two positive values when we plug them in. So let's see what those look like. So when we check out so x equals either 6 plus 6 over the root of 55, or x equals 6 minus 6 over the root of 55. When we look at x equals 6 plus the square root of 6 over 55, this is approximately 6.81 miles. This is outside the scope of our domain, which means it violates our constraint. It violates the constraint where x has to be between 0 and 6. So this is not going to work. So let's try the other one. 6 minus 6 over the root of 55 is approximately 5.19 miles. That certainly fits within our domain. Let's do a quick check to make sure that on t prime of x, if we look at our number line, and remember it's going to go from 0 to 6 now, and we have 5.19 on here. We need to check a couple of numbers in our expression for t prime, which is that crazy 1/8 minus 1/3 6 minus x times 6 minus x quantity squared plus 4 all to the negative 1/2. So when we do that and we plug in a number like 1, we certainly get a negative value. When we put in a number like, say, 5.4 or 5.5, we get a positive value. So we do have a minimum time at x equals 5.19. So indeed, our minimum time is when our visitor or athlete runs 5.19 miles. So we can figure out how much they swim if we wanted to go back and plug it into, there we go, our constraint. We could plug it into this equation and figure out how far they swam. But I think that the question asked us only to figure out how far they needed to run. Oh, yep, there you go. How far should the visitor run before swimming to minimize the time? So all we needed to know was how far to run, and that's exactly what we found. We minimize the time when the visitor runs 5.19 miles. Very, very specific amount here. But that is exactly what we were talking about, 5.19 miles. For the last problem in this section, we're going to look at a ticket price at a theater. And here we're going to be talking about a business application of trying to determine our ticket price that would maximize our revenue. So let's read our problem. When the average ticket price for a concert at the Union Theater was $50, the average concert attendance was 4,000. When the ticket price was raised to $52, the average concert attendance declined to 3,800 people. So determine the ticket price that would maximize the revenue for the Union Theater. So what we need to do here is talk about a few different things. So One is that we have two pieces of information about our ticket prices, and we're going to assume that means there's a linear relationship. So we're going to have to determine an equation for the price in terms of the number of people who attended. So we need to come up with the price, and we're trying to determine the ticket price that would maximize the revenue. So we'll have to talk about how to find revenue here in a moment. So first of all, we're going to talk about, let's find the price, and then we're going to fill in our objective and constraint equations. So to find a price function, and I will tell you this is actually going to be one of our constraints. So to find our price function, we have the points. Now remember, we're going to do our ordered pairs in the order of number of tickets sold or number of people, comma, the price, because we're trying to find an equation that defines price in terms of the number of people who attended the concert. So we have two pieces of information. We had, where was it, 50 and 4,000 go together, and then 52 and 3,800. Notice they were given in reverse order. So we actually have 4,000, comma 50, and we have 3,800, comma 52. So the way that we're going to find this price equation is we're going to have to find the slope, and then we can use point slope. So let's do our slope here is going to be the change in y over change in x. So in this case, the change in price over the change in people. Or 52 minus 50 over 3,800 minus 4,000. Or we get 2 over negative 200, which means that our slope is a negative 0.01. It's a negative 1/100th. So when we go to write our point slope version, I'm going to say that price P, so P minus, and pick one of your points. I think I usually just pick the first one, which is 50, equals M, which is negative 0.01, times, I'll call the number of people in attendance X because I can't use P again, X minus 4,000. So we can solve for P here. P in terms of X here, our price in terms of X is going to be a negative 0.01x plus 1/100th of 4,000 means we're going to move it 2 decimal places. It's going to be 40. And then we're going to add to it the 50 from the other side. So we end up with P of X being negative 0.01x plus 90. And we're going to find out that this is one of our objective equations. We're also going to find out that P, if we think about our price, it's going to have to be greater than or equal to 0. We can't have a negative price for our tickets. We can't be paying people to come to our concerts, right? That wouldn't exactly work. So we're going to add these to our list of objective and constraints. We're going to have to figure out what those are. So our objective here is, it's highlighted here, we want to maximize the revenue. So we want to maximize revenue. And if you're not familiar with business applications, that's okay. I'm going to walk you through how this would work. If you want to figure out how to determine revenue, that's the amount of money you're bringing in. It's not your profit. It is literally just how much money you made through direct sales. So if you think about the relationship between the number of tickets or people attending and the price, you can figure out how many tickets were sold. You can multiply it by the price you sold the ticket at, and you can figure out how much money you brought in based on those ticket sales. So the way that we find revenue is going to be the price times the number of tickets sold, which is going to be X, or the number of people in attendance. So we don't know yet what P is, but we do, right? We actually already found that, right? We started there So that was actually us finding our constraints already. So let's list our constraints then. So we know that our P has to be greater than or equal to 0. If we want to maximize revenue, we really don't want it to be negative. So we probably want to say that R should also be greater than or equal to 0. And we found out that P of X is equal to negative 0.01X plus 90. So what we're going to do now is this just made our problem a lot simpler, especially compared to some of the other problems we've done. Because now we can replace this P of X with this P of X. And we can make our revenue now be in terms of only X. And so it's equal to our price, which is negative 0.01X plus 90, times our number of people coming to the concert, which is the same as the number of tickets sold, X. And while we're at it, we would assume that X is also going to be a positive number. Again, another constraint. And this is all related to the real world scenario in which we are trying to sell concert tickets. So if we multiply through the X so we don't have to do product rule, it makes our lives a little bit easier. So we get negative 0.01X squared plus 90X. And now when we find our derivative, our prime of X, we get a negative 0.02X plus 90. And all we're going to do is set it equal to 0 to find our critical points. In this case, there's only going to be one, because 0.02X is going to equal 90. So X is 4,500. So we're hoping, since it's positive, that that's going to be the magic number of tickets or people, right, that will maximize our revenue. So let's look at our number line. And here is our R prime of X. And let's drop into there 4,500. We know that it has to start no lower than 0. So pick a number less than 4,500, drop it in. Pick maybe 3,000. Well, that would be negative 0.02 times 3,000 plus 90 is going to give us negative 60 plus 90, which is positive. Now, if we pick a number greater than 4,500, like 5,000, we would get negative 0.02x, or times 5,000, which is a negative 100 plus 90. It's going to be negative. So we certainly do find a maximum revenue when the number of people in attendance or number of tickets sold is 4,500. So our maximum revenue is when X equals 4,500 people or tickets in attendance. People in attendance / tickets. But that's not exactly what the question asked for. The question asked us to find the ticket price. So we need to finish this up by finding, so this maximum revenue happens when P of 4,500 equals what price? Well, we plug it back in. P of X is negative 0.01X plus 90. It ends up being $45. So the magic ticket price to maximize the revenue is $45. So quickly here, P of 4,500 is negative 0.01 times 4,500 plus 90, which is a negative 45 plus 90, which is 45. So the ticket price that maximizes revenue is, oops, I misspelled revenue. There we go. Revenue is $45. And that is our solution to this problem.